moments of inertia with respect to shifted axis. We can calculate a matrix of inertia with respect to original coordinate system x, y, z with origin L. Then the pointing vector, displacement vector of elementary mass dm is r, and its value in fact is xi plus yj plus zk. But sometimes we need to recalculate the matrix of inertia or moments of inertia with respect to different system, different coordinate system. So now we will derive the equations how to do it. Okay, I'm drawing now new coordinate system by dash line, so it is x with stripe, y with stripe, z with stripe, and new origin is L with stripe. The feature of this new coordinate system is that axes are collinear with corresponding axis of former system, original system, so new and original system. And the shift vector r we can denote as rs. It's a shifting vector, so rs is definite xs I plus ysj plus zsk, and new pointing vector, displacement vector to mass dm is r L with stripe, or yeah, like this. And generally we ask the question how to recalculate the matrix of inertia of original coordinate system. So originally it was system L, X, Y, Z. When body remains the same at the same position, but we shifted the system, and we need to recalculate the matrix of inertia to new values respecting the system shift. So it is for new system L, X, Y, Z with primes. So how to recalculate values? Let's start with moment of inertia of body with respect to origin of coordinate system. So you maybe already know that JL with stripe or prime is given as an integral of RL prime square dm over all mass. And from simple geometric situation we can say that r, vector r, is given by adding this vector and this vector. So it is rs plus rl with prime. And from this we can express rl with prime that it is r minus rs. and we can substitute it here. So in fact it is r minus rs by r minus rs dm over m. And finally we can write that it is r square minus 2rs by r plus r s square dm over m. Only these values remain with vector properties. This is scalar value is square power of r, and this is also scalar value. Knowing that rs by r, what is this term, is dot product of two vectors, so we can multiply xs, ys, zs by x, y, z. We multiply corresponding coordinates, so it is x, xs plus y, ys plus z, zs. In a component meaning, we can write, for example, that j, y, z is a q. So it is moment of inertia with respect to plane yz with prime in new coordinate system. So it is x minus xs by x minus xs dm over m. So it is integral of x powered by 2 minus 2x xp, sorry, s plus xs square dm over m. What is, if we split this integration into three integrals, so we get integral of x square dm. It is nothing else but jyz minus 2xp, sorry, is xs, because xs is a constant, so we can put it out of the integration, and 2 as well. So there remains integral of x dm, what is static moment, static mass moment s y z, and there remains xs square, integral of xs square by dm, and this is a constant, so we can put it out of the integration, and there remains only integral of dm over m, and it is mx itself, so it is xs square by m. So this is a final result of this integration. We can calculate this, we know it already, we can calculate this. This is static mass moment, and mass is known value. Okay, so analogically we can continue in this way, and we can calculate moment of inertia with respect to plane x, y with primes, and correspondingly we can do it like this. So it must be xy minus 2 zs by sxy plus zs square m, and finally the last value is jxz prime prime, so it must be jxz for original coordinate system minus 2 y s s x z plus y s square m. So by this approach we got moments of inertia with respect to planes of new coordinate system. Knowing that, for example, Jx is equal Jxy plus Jxz, we can substitute for these values from previous calculation. So it is Jxy minus 2zs by sxy plus zs square m plus jxz minus 2ys sxz plus ys square m. So from this we get that it is, we can put together this value and this value, so it is jxy plus jxz minus 2 by zsx sxy plus ys sxz plus ys square plus zs square m. What is finally, because if we add this together, so it's nothing else than Jx, moment of inertia with respect to original coordinate system to axis x, minus 2 by ys sxz plus zs s is xy. I only change order, it's a formal aspect of the calculation, and plus ys square zs square. So this is a result. So if we have mass properties with respect to original coordinate system, Jx, moments, mass moments, statical mass moments, and shift vector coordinates, we can calculate new values for new coordinate system. The same we can do for jy with prime, and it is jy x prime prime plus jy z prime prime, and the result is that it is jy. It is moment of inertia with respect to axis x for original coordinate system minus 2 by y or xs syz plus zs sxy plus xs square plus zs square by m, and jz with prime is jxz prime prime plus jyz prime prime, and the result is jz minus 2 xs square s x, oh sorry, jy not x, jyz plus ys xz plus xs square plus ys square m. So you can see it's not so easy, but it's possible to do it. If you have the mass characteristics for old system, you can calculate by some given way new values of moments of inertia for new coordinate system. And if we consider products of inertia, it's very similar. We can say that dxy for new coordinate system is given by x minus xs by y minus ys dm over all m. And if we make it this calculation, so we got integral xy dm over m minus xs by integral y dm over m minus ys integral x dm over m. So it is finally, this is the product of inertia with respect to plane, or sorry, not plane but axis, with respect to axis xy, okay, xy minus xs by sxz minus ys by syz plus xs ys by m. Yeah, because I forgot here last term, so it is xs ys dm and plus. It belongs here, okay? And analogically we can make the same for this. It is dyz minus ys sxy minus zs sxz plus yszsm, and finally dxz is dxz minus xs sxy minus zs syz plus xszs by m. So we are finished now. So you can say that it is possible to recalculate the old values to new ones, but it's not so easy, it is not so attractive. And it is possible to make it more easy and more attractive for those who make this calculation. So look again back to the first picture. So we recalculated the mass properties of this body from this coordinate system to this new one. And the complexity of this problem you can see here. But there is one possible simplification. Okay, so winning word is simplification. If the origin of coordinate system L, this origin of coordinate system is equal to center of mass. So if it is equal to center of mass, so there some simplification appear. So from this follow that S is equal to 0. What does it mean? That Sxy is equal to Sxz is equal Syz is equal to 0. So all these values are 0. It's a essential simplification. So then JL prime with respect to point is JL plus R square SM. So it was moment of inertia with respect to new origin. Then JXY stripe is JXY plus ZS square M. JYZ is JYZ plus XS square M, and JXZ is JXZ plus YSM square. And also, so these expresses the new moments of inertia with respect to plane for new values and old values. And Jx with prime is Jx original plus ys square plus zs square by m. Jy prime is jy plus xs square plus zs square m, and jz prime is jz plus xs square plus ys square m. So these values are moments of inertia to axis for new coordinate system, and we calculated from old values. And finally dxy prime is dxy plus xsys m. Dyz is dyz plus yzsm, and dxz prime is dxz plus xzm. So there are new values of products of inertia for new coordinate system, and all these expressions, all these formula are called Steiners theorem. So it brought a considerable simplification of formulas above. So now it's easier to use. This is the only consequence of Steiner's idea, that if we don't recalculate two systems between general origin and another different but general origin, but we consider that origin is in fact center of mass of a body, so then we can see this considerable simplification. It makes this recalculation, this style of recalculation, more useful, applicable, and simple. Okay, so if we recalculate the mass properties of body, we are very glad if one origin of coordinate system is equal to center of mass. And how does matrix of inertia look then? So for a new coordinate system, the matrix of inertia is calculated based on matrix of inertia of old coordinate system, but there are some additional terms m by, and there is matrix of additional terms, and there is ys square plus zs square, xs square plus zs square, and finally xs square plus ys square. And here there is minus xs by ys and minus xs zs, and there is minus ys zs. And here, because this matrix is symmetrical, so there is minus xsys, and there is minus xszs and minus yszs. Okay, so there is a matrix form of previous calculus.